my students. They just make the device work. They have the first Germanium 10 terahertz PCAs and the source and detectors, and eventually have the first terahertz Germanium 10 photomixer. So, okay, so 10 years ago in IRM with terahertz, I found that lots of people talking about terahertz gap, and it looks like not anymore. It pretty much like our technology just advanced so much, and you can even get some real-time terahertz imagers or terahertz DDS and very compact ones really on the market, or those those big tech companies like LG, Samsung, Qualcomm that demonstrated their sub-terahertz communication systems even uploaded on YouTube. Okay, but the practical feasibilities of the terahertz systems nowadays still limited by the terahertz sources, and we have to admit that our source is not as good as the nearby bands. Like for the people who work on the microwave regions, they can ship very compact and very cheap microwave sources. When it comes to the higher frequencies, the device parasitics, the RC roll-off, the transit time roll-off just kill off the power. For people who work on the optical side, they can deliver very great lasers, like a laser pointer. I mean, it's so great. But when it goes to the terahertz frequencies, they are trying to manage the material. Okay, so that to make the band gap as several milli-electron volts, those level, and it's very hard to operate it in room temperature. Okay, so then that's what we need. We need the dry, compact, easy to use, room temperature operated terahertz sources for the society. Okay, and for the systems. Okay, so there are another approach go by optical to terahertz conversions. So typically, people use the femtosecond laser to pump the nonlinear crystals to generate the terahertz radiation. And I mean, in a Tuesday, the plenary talk speaker, Professor Lee, he also demonstrated more than 100 million joule intense terahertz pulse pumped by the joule level, like very high power lasers. But if you are looking for the compact solution, the terahertz PCA photoconductor antenna will be a great option to go. So for the terahertz PCAs, it consists of an ultra-fast conductor connected to a terahertz antenna and an external optical pump. When the optical pump is shine on the ultra-fast photoconductor, it generates electrical pairs. And with the bias voltage on the contact electrode is also a terahertz antenna. And then it drifts the photocarriers to the corresponding contact electrodes. The induced photocarriers will drive the terahertz antenna and generate the terahertz radiation. You can operate it with two modes. One with the pulse mode, the other one will be the CW mode. So the first one, you go with the femtosecond laser. It gives you a terahertz pulse and a broadband terahertz radiation. If you go with the two lasers with the separated frequencies, then you can down convert two optical frequencies to one terahertz frequency. So you can fix with one wavelength, tune the other wavelength, and you can get a broadly tunable terahertz radiation. So if you want to achieve high optical to terahertz conversion efficiency with those, the material of the photoconductor is very, very important. You want it to be ultra fast operated. So typically people use the short period lifetime material that kill out the slow carriers. You also want it to be high device pumping efficiency. So you want it to be run fast. So mobility needs to be good. Okay? And you don't want to burn it down. So typically people want to make the device breakdown voltage as high as possible. But you know, these three is kind of contradictory with each other. I mean, if you have the short carrier lifetime material, then the carriers traveling in the material actually is kind of bumpy, right? So then the mobility of the material won't be that good. So typically what people do, they use the MBE tools to grow the material, trying to find the right recipe, right balance between these three. Okay? So at the beginning, people are deciding the right system. So they are going with the 3-5 materials because it's a direct bending material, everything is good. And later on, they play lots of tricks on MPGs, trying to grow like superlative structures and nano islands or rare earth material inside or even transition metal inside. So nowadays, like HHI, they do an excellent job making the terahertz PCAs. And they can even generate almost 1 milliwatt radiation power pumping by 28 milliwatt femtosecond laser. You know, that is a very compact and portable femtosecond laser you can get. Okay, and it's fiber coupled terahertz devices. And later on, actually, we are trying to boost the terahertz power so that we have the idea of plasmonic contact electrode contact to the terahertz antenna, so that we can make most of the photocarriers generated and located near the contact electrode, so that we are significantly reduce the average transport path of the photocarriers to the contact electrode, and we can get very high intensity of current to drive the terahertz antenna. So we can achieve the almost 10% up to 2 terahertz conversion efficiency. And if you go by the LAE, large area emitter concept, and we can generate almost 4 milliwatt terahertz radiation power with a broad frequency range. Okay, so the same concept. Actually, we can go with CW lasers, right? So that we are collaborating with the other research groups, and then they develop the single laser. It's a two-tone laser, okay, 2 colors. And then and also we go with the other chip. It's a Turing pattern frequency cone chip. So we can achieve sub-milliwatt radiated power with the duty cycle operation. So it looks like it's promising to have the terahertz chip and the optical chip integrated on the same platform. Okay, so after almost 40 years development, so right now people are thinking about like chip-sized terahertz systems. Okay, and we are also thinking about this, and we also think about device scalability. Is it possible to make the whole terahertz PCAs, or you can say terahertz photomixer if you operate with 2 lasers? Okay, can we fabricate go with the most compatible processes? Okay, so then we're thinking about why not go with the group foam material? Okay, actually, when we checked it, we found that in 1996, this is the first germanium terahertz PCA developed in University of Tokyo, and then they used the iron to bombard the germanium surface to create the short carrier lifetimes. So make it as short carrier lifetime material, and they had a decent performance and have a decent bandwidth. So in these 30 years, because of the semiconductor industry grows so fast and so big, and the germanium growth, this kind of process is very, very mature. Okay, so that you can have even comparable carrier mobility as the 3-5 materials. So then, in 2018, the HCDR group, and they have demonstrated a very high performance germanium terahertz PCAs. And then it's really good, and even demonstrated very, very broadband terahertz radiation. It's just like, for germanium, this kind of material, still the absorption above 15, 18 nanometers, it just dropped a lot. It just at the band edge. Okay? So then if you go with the short pulse, then it means that it's extending the wavelength range. So a loss of power just is not getting absorbed. So we're thinking like, okay, so how about going deep? Let's go with germanium and tin. Okay? So if you go with germanium tin with higher tin composition, then you can shrink the gap. So this is good. So it means that you have a better coverage of the wavelengths. Also, you're unlocking many laser options. Okay? Most importantly, if you increase more tin composition, it will transfer from indirect bandgap material to direct bandgap material. And the mobility is good. It is comparable with the ultra-fast 3-5 materials, the state-of-the-art ones. So the better news is you can use CVD tool to grow the germanium tin film. And this CVD tool is used in the industry. Okay, so it's very good. So to have the proof of concept, what we are doing is we mix with germanium and tin and we cook it. Okay. we are using a thermal evaporator to evaporate it. And this is not crystalline. I mean, this is amorphous germanium. But, you know, we still can get the ultra-fast response, and you can see the terahertz pulse, and it has a okay, so it gets some radiation, and it has 3 orders of magnitude power lower than the Indian gallium arsenide ones. But you know, this is the first in the world, and you get what you get. And we know how to improve it. Okay, then our second generation terahertz germanium terahertz PCA, we go with the reduced pressure CVD tools. Okay, so we have very, very high quality germanium thin film. And then you can see that this time the carrier lifetime is go to hundreds of picoseconds. Okay, so you can see here the wavelength. This is the absorption coefficient, and it's really expand the wavelength. Okay, and now we get more than 100 times higher terahertz radiation. It's almost comparable with the 3.5 material terahertz PCAs. Okay, so we know how to improve it. Okay, I mean the carrier lifetime is so long, it's so good. So we learn from the history. Okay, so how about giving some doping? Okay, use ion to bombard it. Okay, and to do that, then we can have ultra fast operation. It's very good for the terahertz PCA detectors and also terahertz photomixers. Okay, so yeah, so this is our terahertz PCA detectors, and you can see that we go with different doping concentrations, and you can see the material properties. And right now, you can see that the carrier lifetime just goes so low, it can reach to the sub-picosecond level, and we can have a decent mobility decrease. I think that is acceptable, so that you can see that we can, yes, this is the first germanium terahertz detector, and then it performs much better than the intrinsic one, the one that will have a longer carrier lifetime. And this will be a very good material for the terahertz photometer. And it should be noted that this device, we use the CVD tool to grow it. We grow it on an 8-inch silicon wafer. So we can have more than 100,000 terahertz pieces on the same wafer, and it is very cheap. Okay, so then yes, we play with the formation, we play with the recipe, play with the doping level and the doping and the driving energies, and then we get the first terahertz germanium tin photomixers, and it can have a good tunabilities. But it should be noted that it's because we are using the Toptica TerraScan, this equipment, and then it's limited by the separation frequency we have. So yeah, so that will be the end of my talk, and if you have any questions, just let me know. Thank you.
Yeah, thank you very much for this exciting talk on this germanium tin photometers. Is there any questions in the audience?
Can you go back to the plot you were showing the time trace of the germanium yeah, exactly this one.
Which one?
The next one.
This one?
Yeah, so in the time trace that you were showing the one, the 3.5 one has this other pinkish, the black one, the Harvard's reflection.
You are showing, you're talking about this? The
Yeah.
time domain
So
signal?
this is the one that you're comparing with your device, right?
Exactly, yes. So this is a time domain signal, frequency domain, so you can see it's a higher power than the germanium ones.
And the thickness of, how is it, the thickness of these two compared to each other? Like,
The thickness of the material? It's around, I think it's 280 nanometers. Yes.
Okay, and because in the previous ones you were showing that even yours has higher, it's showing a higher thermal signal, but in this one, suddenly, I don't know, it's
Oh, not
right
really.
side.
So
Kind of switch.
let's see. So in in here you can see the black one is the 3.5 device, and then the blue and the red one will be germanium and germanium device. Which one you are mentioning?
The one.
Here?
Yes.
So, okay,
So,
so this one I even timed with 50, and then it's here.
okay, this is the first
And
device.
this is the-
Okay,
Yes.
okay, thank you.
You showed a graph there where there was a dark current with respect to the non-dark current. A few slides up.
So on the last slide,
I think it was something like that. Maybe next here.
here,
No, sorry, this one. These
Yes.
two graphs, dark current and photocurrent.
yes, so we separate them. So this is photocurrent without current. Yeah, so this one is really depends on, shows the resistive, kind of resistivity. Yeah.
Yeah, but does that mean that it warms up a lot, or doesn't that mean that there is a lot of thermal heating?
Yes, actually, but that is kind of comparable. But I won't say it's really much better than purified materials. Yeah, and that one actually, if you go with different process. So for example, we are doing iron implantations to change the material. That is a post-processing process. So then you can see the resistivity changes. So then we are trying to increase the resistivity. Yeah. So then we can have lower dark current. For the emitter, then that's good, and we can drive with higher voltage. For the receiver, then we have less noise. Right.
So thank you very much. I mean, growing photographic 3D is really impressive, though I'm a bit skeptic about your numbers. First of all, resistance is fairly low, and I don't think it's going to get much better if you do ion implantation. French people like Lampin and so forth, they have done this years ago and never worked out to get a high resistance material because it creates such a lot of undesired perturbations that the resistance always remains low. And then I have a question to slide 17. May you compare it to a 3.5? I mean, the 50 dB dynamic range, that's state of the art of 2008 or something. I mean, nowadays 3.5 devices have 110, 120 dBs. Is that a fair comparison here?
Yeah, actually, yeah. Thanks for your question. So for this one, we are not comparing with the commercial device. Those devices, we made it. So we grow the 3.5 material, and then we have the same device on top of it, and we compare. Yeah, so it means that our MBE, we are not doing a good job on that. Yeah.
Well, it's a matter of decades of optimization, so don't worry.
Yeah. So then, so definitely nowadays you can get like 80 dB, 100 dB SMR signals. But for ours, yeah, it's like 50-ish, 60. Yeah. And we prefer to go with that way to have a fair comparison.
All right, with this, I think we always serve some coffee, and we close the session. We'd like to thank all the speakers.